Hello, this is Firyuza, and you are watching Bold Science with Firyuza. Today we are traveling to a moment when physics took a sharp turn and the familiar picture of matter literally crumbled before our eyes. This is a story of how one person dared to say, if light behaves like a particle, then a particle must behave like a wave. And that person was an ordinary graduate student. Louis de Broglie, a young, quiet and extremely modest French researcher, was studying works by Planck and Einstein. They had shown that light, which for centuries was considered a wave, possesses particle-like properties, momentum, energy, the ability to strike matter. And suddenly de Broglie asked a heretical question. If a wave can be a particle, why can't a particle be a wave? This wasn't just a philosophical move. He set out to build rigorous physics, a bridge between two incompatible worlds, the world of particles and the world of waves. He looked at the photon. A photon has energy, momentum. This momentum is related to wavelengths lambda, so the momentum and wavelengths are linked. And then de Broglie took a radical step. Any particle with momentum p must have its own wave with these wavelengths. Any particle, from an electron to a molecule, to a speck of dust, to you and me. Only for large objects, the waves are far too small to observe. It was an explosion. Physics wasn't ready for matter to oscillate. And now the magic of science begins, the experiment. Electrons were passed through a nickel crystal, and what appeared on the screen? George Paget Thomson and the son of J.J. Thomson, who had discovered the electron as a particle, proved the opposite. The electron is a wave, and not just any wave, but one producing beautiful diffraction rings. The irony is that the father discovered the electron as a particle, while the son revealed its wave nature. Both received Nobel Prizes for opposite properties of the very same object. The wave nature of molecules and atoms was discovered. All of them produce diffraction patterns, which means wave properties are universal for all matter. Bohr had once proposed a strange idea. An electron in an atom can move only along allowed orbits. But why? He couldn't explain. De Broglie gave the answer. A stationary orbit is an orbit where the electron fits onto itself like a standing wave. If the wave closes on itself with an integer number of wavelengths, the orbit is stable. If not, the wave breaks down, and the orbit cannot exist. Thus, the wave nature of matter explains the stability of atoms, one of the most mysterious features of the quantum world. De Broglie's hypothesis became a foundation for Schrödinger's equation, for all of quantum optics, for the tunneling effect, for modern electronics, for microscopes sensitive down to individual atoms. Every transistor, laser, and microscope, all of them rest on the wave properties of matter. But in 1923, this sounded almost insane. De Broglie sent his work to Einstein. Einstein read it and said, "There is something to it," and he supported it. And 2 years later, experiments confirmed everything down to the last detail. Today, de Broglie's idea sounds natural. We're used to thinking of particles as waves and waves as particles. But when it first appeared, it was a bold turn that opened the door to a new world, the world of quantum mechanics. Thank you for being with me on the channel Bold Science with Firyuza. See you in new scientific stories.